Hello, I'm Jesse Rogers, and I'm a college math tutor. This is 13-year-old Mira's homework, and I told her grandmother that I'd help with it. But before I do, I have to say a few things. The approach I use may or may not be the way that the K through 12 teachers use to solve these problems in class. For years in Florida, we've had a teaching paradigm called Common Core. And now, because the politicians in charge are different, we're in the process of switching over to a different teaching approach called BEST. But no matter who is in charge or what legislators demand teachers to teach, I hope you don't take that too seriously. If what people tell you is that you have to solve things their way and that solving it any other way is wrong. There are many ways of looking at and solving problems, and math is all about finding creative, interesting, useful ways of getting to the answers we need. By contrast, what you're often taught in math classes is that there's only one path, and if you solve things any other way, you'll get a big red X on your paper. At least math classes that have been politicized. Well, it's little wonder that many people grow up to hate math or to think that they're not good at it, because that's generally the approach that American students are subjected to. You're not being taught mathematics. You're being taught obedience, compliance, hollowed out procedure, powered by memorization exclusively with so much of the discovery, so much of the fun removed. My advice is not to argue with or blame your teachers. None of this is their fault. They're collateral damage in a culture war, doing whatever they're trained to do and saying whatever they're forced to say as part of a much larger system that rewards obedience and conformity more than independence and discovery. But in your heart, always remember that it's all just a game. For real mathematicians, winning is not about getting a perfect grade or a teacher's approval. Winning is about the thrill of learning how the world actually works. It's the power of using that knowledge to make accurate predictions. That's what mathematics is really all about. It's why so many rich and powerful people are good at mathematics and why so many mathematicians are rebellious and hard to control. As an example, I can guarantee you there's a lot of people in charge that would not want me to say any of what I've just said to a 13-year-old. But can they control me? No. All right, so now Mira and everyone else, I'm going to give you my ways of doing this homework, which I hope you'll find helpful. But again, please know these are not the only ways to solve these problems. I'm not going to start with the first problem actually here about Landon. We're going to scoot down to Jasmine. Jasmine can run 4 5/6 miles in 2/3 of an hour. How many miles can she run in 1 hour? And my approach with this is to use a formula that is distance equals rate times time. So this is the formula that generally describes motion. And so if Jasmine is running 4 5/6 miles, when it has the unit miles, what are we talking about there? Which one of those three would that fall into? 4 5/6 miles. That's going to be the distance, right? So 4 5/6, that's going to be the distance. What about that 2/3 of an hour, right? We have 2/3 of an hour. Hours are units of time. So that's going to go in for time. How many miles can she run in 1 hour? So miles per hour is how we measure rate, right? So that is the rate. That's what we're trying to solve for. So this is actually an algebraic equation. It may or may not be presented as an algebraic equation, but that is how we could look at it. And so what we're going to do is we're going to take the distance of 4 5/6, put that in the place of the distance. The rate is what we're looking for, and we're going to use the variable x to represent that we don't know what the rate is. And the time is 2/3. So this is going to be times 2/3. All right, so now when we want to solve for x, what we have to do is kind of unwind everything on that side of the equation so that we just get x by itself. So we have to get rid of this 2/3 because that's modifying the x, right? We don't want 2/3 of an x, we want 1x. So what we're going to do is we're going to change this equation by multiplying both sides by the reciprocal. So the reciprocal of 2/3 is 3/2. We're going to multiply this side also by 3/2. And so the 3's can cancel and the 2's can cancel. By canceling in multiplication, what I mean by that is that 2 goes into 2 one time and 3 goes into 3 one time. And so this is really the same thing as just 1, right? So cancellation, when you hear people say they're canceling and it's multiplication, what they mean is that it becomes 1. So this is x times 1. And we don't really need to put that times 1 because it's understood that we're talking about 1x if all we see there is x. So this is now x equals, we've got to deal with this fraction, this improper fraction multiplied times a mixed number. So what we're going to do is we're going to take this mixed number, and I'm actually going to turn this into an improper fraction. I find that easier to work with. So 4 times 6 is going to be 24, and then I'm going to add the 24 plus the 5. So that's going to give me 29 over 6 times 3/2. And I see, before I even go through and multiply this, I see that I have a 3 on the top and I have a 6 on the bottom. And I know that 6 is 2 times 3. So because there's a 3 on the bottom and there's a 3 on the top, 3 goes into 3 one time. So that could be 1, right? That would cancel out. And so now this is going to be on the bottom, just a 2 that survives over here. So when we multiply fractions, we do bottom times bottom and top times top. So this is now just a 1 up here. And so 1 times 29 is going to give me 29. And then on the bottom, 2 times 2 is going to give me 4. And so that's my answer. But if you notice, the format that they're asking for does not have an improper fraction. It's got a mixed number as the acceptable format. So what we're going to do is we're going to take this 4 and we're going to divide it into 29. How many times does 4 go into 29? So it goes in 7 times. 4 goes into 29 7 full times. That's because 7 times 4 is 28. So if you're dividing this, we could do this by hand, or you could use a calculator, depending on what your teacher lets you do. But I think it is good to get the practice, especially if you're not doing this in a testing situation where you're going to be punished for getting a wrong answer. It's good to practice and just do this by hand too. So 4 times 7 is 28. And when we subtract 29 minus 28, we're going to have a remainder of 1. And that remainder goes on the numerator, the top, and the 4 goes on the bottom as the denominator. So 7 1/4 is how many miles she can run. How many miles she can run if she runs for 1 hour. So that's what that rate is. That rate is if it's 1 hour, because remember that we were talking about miles per hour, miles per 1 hour. So she can run 7 1/4 miles in 1 hour. All right, so that's how that one goes. And I'm actually going to use the same idea to solve this problem above, even though it doesn't necessarily have to do with a distance, right? Landon was taking a math test. He finished 1/2 of the test in 3/5 of an hour. How much of the test will he have done in 1 hour if he keeps the same pace? So we're talking about pace. That's still kind of like a rate, right? And the taking of a math test, we wouldn't usually think of that as a distance, but we could, right? We could think of, he's got his start, right? And he's taking the test and he's, you know, uh, knocking over problems just like he might knock over a goalpost if he's doing a 100-meter dash or whatever the case is. So he's finishing each of those problems. He's getting halfway there, right? So he's moving along, and he starts and he gets halfway, and that's how far he can get in 3/5 of an hour. So what we're going to use is that same formula, distance equals rate times time. It's a really powerful general purpose kind of formula. And so, you get to use these things a lot, and you do memorize. It is good to memorize formulas, but you want to know why you're using it, so that you know where to use it, and you want to be able to isolate X. That's a really powerful, uh, you know, ability. If you can solve equations in a really general way, then you can apply it to a lot of situations. So you can see that this, again, doesn't necessarily have distance, so I'm applying a concept to something where it would work, but it's just different language that they used. So Landon was taking a math test. He finished 1/2 of the test. So that's going to be going in for our distance. That's what we're visualizing as being distance. And then the rate is still what we're going to be trying to discover, because we're talking about how much of the test will he have done in 1 hour if he keeps the same pace. So again, pace, that's a key word that means rate, same thing as rate or speed. And so this is analogous to miles per hour, but instead of miles, it's going to be like tests per hour. So how many tests can Landon do per hour? So testing per hour is going to be the rate, and then the time. In our situation here, where we finished 1/2 of the test, was 3/5. So this is going to be 3/5, replacing the time. So now we've replaced the distance. We've identified that our variable that we're solving for is X, the rate, and we've replaced the time. So now, again, to solve for X, what do I have to do? I have to get rid of this fraction here. How do I get rid of a fraction? I can multiply both sides of an equation by its reciprocal, because whatever I do to one side, it's fine for me to do that as long as I do it to the other side of the equation too. So I'm going to multiply this exact same value on both sides of the equation. And 3 divided by 3 is 1. 5 divided by 5 is 1. So on this side, I'm just left with X. And then over on this side, I have 5 multiplying times 1, 3 multiplying times 2. I don't see anything that I can cancel, so I'm just going to go ahead and do those multiplications, and I get a numerator of 5, and I get a denominator of 6. And they already put the 5 in for us, but they just wanted to know what would that denominator be. And by using a little bit of algebra, we have been able to identify that that is a 6. All right, so now let's go down to the next problem, see what else we've got. Let me clear this. All right, so William ran 2 2/3 laps around a track in 4/15 of an hour. If William keeps the same pace, how many laps could he run in 1 hour? So once again, we're doing a rate here, right? How many laps per hour is what we're trying to discover here. So instead of miles per hour, this is laps per hour, right? But it's still a rate. So we can still use this distance equals rate times time. And we're going to replace the distance that he ran. So the distance was 2 2/3. That was the distance, how many laps around a track. And 4/15 is the hour. So that's going to go here under time, 4/15. So, and the rate is what we're trying to solve for. We don't know what the rate is yet. We don't know how many laps per hour William can do. But we're going to go ahead and identify what that is shortly. What we have to do is multiply by the reciprocal, right? Because we're trying to get X by itself. So to get rid of this part that's not X, we're going to multiply by the reciprocal. That's how we unwind that part there. All right, so we're going to get rid of this on the right side of the equation, and we have to multiply it on the other side to balance it out. We have an improper fraction multiplied times a mixed number. It would be easier to make that an improper fraction times an improper fraction. So we are going to go ahead and turn that 2 and 2/3 into a fraction by multiplying 2 times 3. That's going to be 6. And then adding that to the 2 that's on top here. So 6 plus 2 is going to be 8. The denominator stays the same, so that's going to be 8/3. So 8/3 is the same thing as 2 and 2/3. We're going to multiply this times 15 over 4, and a lot of people will reach for the calculator, but let's see if we can do some cancellations first. So on the top we have an 8, on the bottom we have a 4. 8 is 4 times 2, so 4 goes into 4 one time, meaning that we can get rid of those 4s. 3 goes into 15 how many times? 5 times. So we get rid of those, and that's going to be a 5. So now we've got 5 times, that was a 4 that had canceled out, so it's gone now. So 5 times just the 2, right? So this is going to be 10. And the bottom is 1 times 1, so it's just going to be 10 over 1. But we don't really have to write that over 1 because it's understood. So sometimes when we're multiplying fractions, it's easier to turn a whole number into a fraction. But by just dividing by 1, 10 divided by 1 means the same thing as 10. But in this case, it's easier for us to keep it as a whole number, I think. So we're going to go ahead and write it that way. So this is going to be 10 equals, and we've got x. Remember that x was, the units for x would be laps per hour. So 10 laps is how many laps could be run in 1 hour. All right, great job, William. Now let's go on to our next runner, which is Clay. Clay can run 1 lap around the track in 1/4 of an hour. How many hours will it take him to run 5 1/3 laps around the track? So I've still got this formula, distance is equal to rate times time, and that is still defining the motion that Clay is experiencing here. So now I just need to line up my variables, and they might have given me different variables here. Clay can run 1 lap around the track in 1/4 of an hour. How many hours will it take him to run 5 1/3 laps around the track? So 5 1/3 laps, is that going to be a distance? Is that going to be a rate? Or is that going to be a time? I'm going to put that in as a distance. So I've got the distance here, 5 1/3 laps. Five and 1/3 laps. And then the rate is actually something that they gave us in this problem, whereas before they had been giving us the time. This is asking the question, how many hours will it take him to run 5 1/3 laps around the track? So how many hours means that we're trying to solve for time. This is our unknown variable. So that is where I'm going to put my x. They did give us the rate in this case. They gave us the rate of 1 lap around the track in 1/4 of an hour. So the rate is 1/4. Ooh, wait a minute. This is tricky. This is tricky. Clay can run, if we're doing this in laps per hour, if that's how we're thinking about this, because that's really what we're trying to find is how many hours it'll take. So we're using a unit of hours, and we have 5 1/3 laps. So laps per hour is really what we're working with here, right? Well, if he can run the track in 1/4 of an hour, and that's 1 full time around the lap, or 1 full time around the track, then how many could he run in 1 hour, right? Because If we use this formula again, let's say distance of one lap around the track is equal to whatever his rate is, and the time is 1/4. So we're actually going to have to discover, we are going to go ahead and discover the rate here. So what do we have to do to get x by itself? We're going to multiply by 4 over 1. 4 over 1. And I'm having to do this because they didn't give me the rate in laps per hour, which is what everything else is being measured in, laps and hours. They gave me that Clay can run one lap around the track in 1/4 of an hour. And I have to discover from that he runs, that X is going to be 4 laps per hour. So I'm going to put 4 here as the rate, laps per hour. Okay, so now how many hours will it take him to run 5 1/3 laps around the track? So now I'm going to multiply both sides by, this is 4 over 1. We could think of it as being 4 over 1 by turning it into a fraction. And so I'm going to multiply it by its reciprocal, which is going to be 1 over 4. I could divide by 4. That's another way of approaching this, but I'm going to go ahead and multiply by a fraction because when I'm dealing with mixed numbers and fractions, that's just an easier thing to do. So 1/4 is going to be multiplied times. To turn this into a improper fraction, we're going to take 5, multiply it times 3, that gives us 15, and then we're going to add the 1. So that's going to be 16 over 3. And this is going to be x. And remember that x was a unit of time, right? So x is still there as our unit of time. So 16 divided by 4, that can be reduced so that we're just going to have a 4 on the top. So 1 times 4 is going to be 4, and 1 times 3 is going to be 3. So x is going to be 4/3. Now, that's an improper fraction, and they are expecting a mixed number. So we have to rewrite this as a mixed number. So 3 goes into 4 one time. 1 times 3 is 3. I'm going to subtract that. So 4 minus 3 is 1. And so this is going to be 1 1/3. So that would be our answer. 1 1/3 hours is how many hours it would take him to run 5 1/3 laps around the track. All right. That's actually all I'm going to have time for right now. I know there's a few other problems, but hopefully after we discussed the first problems, that'll give you an idea of how to do the other ones. All right, so I'll leave it to you guys, and good luck on your math problems. And remember to try to discover your own way. Don't just accept that there's only one way to do things. All right, Jesse out. Have a great day.